Good morning, welcome back to Springs. In the third video, we discuss about rectangular cross section, square cross section and disc springs. Three of them we'll do it in the third one. Fourth one we'll discuss in about leaf springs. In one video one, we have discussed about the symbols and procedure. In the second part, we did circular cross section springs. Now we will do rectangular cross section, square cross section and disc springs in this. A rectangular wire is taken and a spring is formed. The rectangular cross section has got two dimensions. One is the width of the cross section, thickness of the cross section h, width is b. Whereas a square cross section, both are equal, b and h are equal, is a special case of rectangle where b equal to h. Then coming to your disc spring is like a washer with a dished shape, dome like thing will be there, and it gets compressed and give you very small deflection for very high load. The last one in the next video we will talk about leaf springs separately. The helical springs, the most of the symbols are same. Tau is the allowable shear stress, G rigidity modulus, then we have tau y is the elastic limit, torsional elastic limit, which we get from the table for different materials. Table 20-10, page 2015, different materials. There are two properties given, tensile properties and torsional properties. For helical springs, we use torsional properties. For leaf springs, we use tensile properties. G rigidity modulus, as usual, whenever it is not given, we take about 80,000 MPa for steels. Then F0 is stiffness, is load per unit deflection. F is the load, Y is the deflection under load. The ratio of F by Y is called as stiffness. P is the pitch, is the distance between two coils. LW is length of wire required to manufacture the spring. Rectangle has got two dimensions, B and H. Since two unknowns are there, a ratio between B and H will be given. Sometimes H is 2B, sometimes B is 2H, like that. Some ratio is given, 1.5 times, 2 times, like that. The ratio of the sides is given to us, and the load as usual F, spring index C, required deflection, allowable stress, rigidity modulus. These five are common for all the springs. In addition, for a rectangle, sides ratio is important for us. B and H are the sides, and always H is the side parallel to the axis. This is H, which is parallel to the axis. H, B is side perpendicular to the axis. Please remember, it is not horizontal vertical. H is always side parallel to the axis. B is side perpendicular to the axis. Should be careful in the problem what is what given. Then H may be big or B may be big, we don't know, but H is always parallel side, B is always perpendicular side. In this figure it is shown as if H is bigger than B. Sometimes B will be bigger than H, we don't know how the problem is given. D is the mean coil diameter. So as usual, there are 7 steps in the design. Step number 1 is to find the cross sections. That is, here we have to find B and H using the shear stress equation. Step number 2, mean coil dia, inside dia of coil, outside dia of coil. Step number 3, deflection. Step number 4, free length of the spring. Step number 5, pitch. Step number 6, stiffness. Step number 7, length of wire. What we have done for circular cross section, same steps here. Since the cross section is different here, the equations for tau and y are totally different here. The equations for tau and y, we will see what is given for rectangle. Page number 20-9, equation number 34a is the shear stress equation for rectangular cross section. KFD 1.5H plus 0.9B by B square H square. This is equation valid for rectangular cross section. The same equation, if you want to use it for a square cross section, B equal to H, substitute B equal to H in this equation, it will result into square cross section. That is given separately. We discuss in the next problem. So in this equation, K as usual for any helical spring, K equal to 4C minus 1 by 4C minus 4 plus 0.615 divided by C. This is same for all the types of springs of helical in nature, round cross section, rectangle or square. For rectangle it is given separately again, 2036 page number 29, which is same for circular cross section. Only thing is C should be very careful. It is d by h or d by b, whichever is small in the denominator it is used here. If b is small, b is used in the denominator. If h is small, h is in the denominator. So C equal to d by h if h is less than b, C equal to d by b if b is less than h. Be careful about the selection of C. It should be either d by h if h found to be small, if d by b if b is found to be small. Here in this figure you see that b is smaller than h, h is bigger, b is small, so we should use this part, C equal to d by b, like that, and substitute these values. In terms of h we will put it as 2b or 1b, like that. Then we find the cross section width and thickness b and h as the first step. Second step, mean coil diameter, either d by b or d by h depending on whichever is small, we have seen earlier. Depends on the C equation. C may be d by b or d by h. Then outside diameter of the coil d plus b, inside diameter of the coil d minus b. Then third step is the deflection equation, which is different for a rectangular cross section given in page number 11, 20-39. 2.83 IF d cube b square plus h square by b cube h cube g. This is a different equation for rectangular cross section. If y is given, we find I. If I is given, we find y, like what we have done in the earlier cases. Right. Then after knowing the I value, we find out the free length, the height of the spring free from the load is called free length. I plus n into h plus y plus a. This equation is similar to what we have used for circular cross section. Only thing is here we had used as d. Now it should be h here. H is the height of the spring here. I plus n into h plus y plus a. Here n is always used as 2 because we assume that square and ground ends. Always we take n equal to 2, and a is the clearance. We always assume clearance as 25% of the deflection, 0.25 into y. So we find out the value of the free length. Then we go to pitch. Pitch is L0 minus 2h by I, not 2d. In a circular cross section it was L0 minus 2d we had used. Now it should be 2h by I. Then stiffness, F0 equal to F by Y, same. Length of wire is, the total length of wire is length of one coil pi d into total number of coils. Length of wire equal to length of one coil pi d into I dash. I dash is I plus n. N we always take as 2. So these 7 steps are similar to the circular cross section, but equations for y and tau are different. Be careful about the cross section and select the equations. Then we do one square cross section. When we go, only difference is b equal to h. You can see that it is square, both sides are equal, and it's called as h only. Both are called as nothing like b, both are called as h only. B equal to h here. If you substitute these values in the equations of rectangle, they simplify to, the tau equation simplifies to 2.4 kfd into h cube, and deflection equation simplifies to 5.66 IF d cube h power 4 by g. They are given separately in page number 12, 2043 and 2044 for square cross section. Everything else is same like earlier. B equal to h is the only thing for square cross section. We'll do one problem on rectangular cross section. Design a helical compression spring of what cross section? Rectangular cross section, for a spring loaded safety valve. This is similar to our second problem what we did in the round 1. The application is for a safety valve. The data are different here. Operating pressure, that is safe pressure, is 0.7 MPa. Maximum pressure when the valve blows off freely, it breaks, is 0.8. When the valve lift is given, when the pressure reaches 0.8, when 0.7 to 0.8 it increases, the pressure increases from 0.7 to 0.8 MPa, the valve will lift by 5 mm. The valve will lift by 5 mm. Diameter of the valve seat is required for us to find the force. Diameter of the valve seat is 90 mm. Allowable shear stress 320. Spring index is 6. Please note this. The long side of cross section is twice the short side. That means sides ratio is 2. Long side by short side is twice. Twice is 2. Which is long side? We have to see further. The spring is formed with longer side parallel to axis. The side parallel to axis is the longer side. That means we remember always the side parallel is H. H is the longer side and B is shorter side, and H by B equal to 2. So this sentence is very important for us for rectangle. The long side to short side ratio is 2, and the spring has got longer side parallel to the axis. Parallel to axis is always H. So the data I have listed here: P1 minimum pressure, maximum pressure, lift during the rise of the pressure, valve seat, diameter of valve seat, allowable stress. Rigidity modulus is not given. We have taken 80 GPa, 800 MPa. Spring index C. Long side is parallel to axis. Side parallel to axis is always H. So H is the long side. H is greater than B. Therefore sides ratio equal to 2 is H by B. H by B. Since B is small here, spring index C equal to D by B. This denominator should be small always. Suppose if H is small, then it becomes D by H. Since here B is smaller than H, spring index is D by B. Smaller value in the denominator. First we have to find out the force acting, like earlier what we have done in the case of circular cross section. Force acting on the spring is nothing but force acting on the valve seat, the pressure. So area of the valve into pressure is the force. Area of the valve is pi d square by 4 into the pressure. Since we have two pressures here, we are going to get two forces. Minimum force is corresponding to minimum pressure. Pi by 4, 90 square by 90 square pi dV square 90 square by 4, this is the area, into the minimum pressure 0.7. Similarly, maximum force is the same area into the maximum pressure. So now we have to find out maximum deflection from this relation, which we have used earlier also, 2031 page number 20-9. Maximum deflection y2 equal to f2 y dash by f2 minus f1. F2 is this, f1 is this, y dash is given, lift is given as 5 mm. So the maximum deflection comes to around 40 mm for this problem. Now we have to design the spring for maximum load and maximum deflection. Maximum load on the spring is F2, maximum deflection is Y2, which is Y, allowable shear stress given in the problem, G is given, spring index is given, and please remember D is 6 into B, not 6 into H, because B is small here. So take tau equation for rectangular cross section. KFD 1.5H plus 0.9B by B square is square. Substitute H, first find K. K usually same equation, 4C minus 1 by 4C minus 4 plus 0.615 divided by C. We get K value as 1.2525. Then substitute H equal to 2B in the earlier equation, all these equations. And capital D we have to substitute as 6 into B. 6 into B for capital B. H as 2B. We can find the value of B as 11 mm. 10.79 we rounded off to 11 mm. Then H becomes 22 mm. Then main coil dia, same, C into B. Outside dia of the coil, D plus B. Inside dia of the coil, D minus B. So we get these three values. Then deflection equation for rectangular cross section is different. In page number 20-11, 20-39, for rectangular cross section, 2.83 I F D cube into B square plus H square by B cube H cube into G. We know all the values I except I. He has given the deflection. We can find out the number of coils I. I is coming as 18.1, say 19 coils. Then free length L0, I plus N into H, plus y plus a. N is always 2, assuming square and ground ends. A is clearance, always taken as 0.25 into y. So L0 comes to 512. Then pitch P equal to L0 minus 2h by I, stiffness F by Y, length of wire pi d I dash. I dash is I plus N. I plus N is I dash, total number of coils. So this is the end of the first problem. Then I have taken one square cross section problem. Design a helical compression spring of square cross section to support a load of 3 kilonewtons. The deflection under load is limited to 60 mm. Spring index is 6. Allowable shear stress is 345 MPa. Modulus of rigidity is 80 GPa. So here it's a, well, this is something like your first problem what we have done in the circular cross section. Only difference is the cross section is here different, square. Load is given, deflection is given, spring index is given, allowable shear stress is given, G is given, and it is a square cross section. Square, there is no confusion. Square C is always D by H. Only one dimension is there, B equal to H. So CD equal to 6H. So with this data, use the different equations of tau and y which are given for square cross section. Complete the problem trying the 7 steps what you have done earlier. Please try this as an assignment. I conclude that the values of the equations for tau and y are different for circular cross section, rectangular cross section, and square cross section. Other things are all same. Be careful about 7 steps you have to do. Selecting the equations for tau and y depending on the cross section. If nothing is given, it is always circular. If it is a rectangle, then make sure that which side is parallel to axis, which side is perpendicular to axis, then we get the sides ratio. Side is always parallel to axis is H for rectangle. Right. So with this, the problems of square and rectangle, please try at home. Then comes to the second type called disc spring. It's also called as belly spring. The symbols is like a hat here. You can see like a hat here. There is a gap here. T is the thickness of the plate that we use for manufacturing this. Inside diameter, outside diameter. It's like a circular piece. We have got a hole here, inside diameter, outside diameter. See this here, how they are stacked here to get more deflection. One is above the other. They have placed it like this. So many springs are there. D naught outside dia, Di inside dia. T is thickness of plate. Important is H. H is the height of the gap here. This H is also called as dished height of the spring. The dome height up to the inside, not outside. Up to the inside, the height is called dished height of the spring. That is the gap between the bottom and the inside of the spring. F is the force. E is modulus of elasticity. Extra what we get is Poisson ratio. Poisson ratio is 0.3 for steels. And E value if not given, we take 200 GPa for steels. All this we have been doing earlier also. M, C1 and C2 are 3 constants which are to be selected while calculating. I'll show you a graph and tell you how to select these constants. They depend on the ratio of Di and D naught. See this figure here. This is given in our data handbook page number the equation table number 20-3 page 20-6 here. We have got the figure like this. The x-axis is D naught by Di, outside dia by inside dia. Just for example, if the ratio of D naught by Di is 2 is here, 1.5, 1.75, 2 is this line. Go along this, and there are 3 curves here, one for C1, one for C2, one for M here. And C1 and C2 are to be selected from y-axis right side. M should be selected from left side of the figure here. Suppose D naught by Di is 2. Touch this curve here. Read the C1 value as 1.2 on the y-axis. I repeat, 2 is the ratio of D naught by Di. Go touch the first curve. Read on the right side that C1 value is 1.2. This is C1 curve. Similarly, 2 go up, touch the second line, which is C2 line. Read the value on the right side. It is 1.2. This without any number, this line is 1.3, x 1.4, and this value is somewhere around this here. It comes to maybe 1.35 or 1.36 approximately. Similarly, at the same 2, touch the M line. Read the value on the left side. It is between 0.6 and 0.8, say 0.7. Like that, we will select the values of C1, C2 and M. C1, C2 are to be taken on the right side of y-axis, M on the left side of y-axis. There are only 3 equations relevant to this disc springs. One is the force equation, 4 Ey, Young's modulus, deflection. This nu is Poisson ratio, M is a constant, H is the dished height, Y is deflection, T is the thickness. Force equation is given in page number 205. Equation number 2019 is the last equation in that page number 205 for disc springs. This is the equation for force. Then stress at inner radius, stress at outer radius, 2 equations are given. These equations are identical except in the bracket you see that this is plus C2T, here minus C2T, otherwise everything else is same. The equation is same for inner radius and outer radius except this value is plus here and minus here. These equations are 2021, 2020, page number 20-6, first and the second equations. By virtue of this algebraical equation, this first value sigma I is always greater compared to sigma O because this is added here, it is subtracted here. So this entire value is more compared to this value. So allowable stress should be always taken as sigma I. Let's see one small problem. Design a belly spring made of 3 mm steel sheet. The thickness of the sheet is 3 mm. This is the thickness 3 mm with inside and outside diameters as 50 mm, 130 mm. Inside diameter 50 mm, outside diameter 130 mm. The dished height of the spring is 5 mm. This gap from this line, inside line to this inside, this gap is 5 mm. So maximum we can compress by 5 mm, then it becomes flat. The allowable stress for the spring material is 600 MPa. Allowable stress should be always taken as sigma I, that is given as 600. You have to determine the load that should be carried, the deflection, the stress at outer edge. One dimension is given, we can find the other two here. One is the safe load, other one is the deflection. Then what is the stress at the outer side? Let's see the figure again. The data given, thickness 3 mm, inside dia 50 mm, outside dia 130 mm. The height, dished height, no, from inside to inside, this gap is 5 mm. Allowable stress is always sigma I, 600 MPa. Two dimensions are not given. Young's modulus we take 200 GPa and Poisson ratio 0.3 for steels. What we know is sigma I. So we start from sigma I. Before that we select the constants from the graph. We have seen this figure 20-3 page 20-6. Earlier I told you this graph selection. Now let's see what is d0 by di. d0 is 130, di is 50. The ratio comes to 2.6. For this 2.6 on the x-axis, this is 2, this is 2.5, this is without any number, this line is 2.75 in between. 2.6 is between 2.5 and 2.75 somewhere here. So this is the line at 2.6. 2.6 we touch this graph. C1 we take on the right side. It comes somewhere here. So 1.2, 1.3, 1.4, slightly more than 1.4. For 2.6 it comes somewhere here. So the value of C1 will be 1.34. I have taken approximately. It is more than 1.3, less than 1.4. Similarly, same 2.6 somewhere here. Touch C2 line. Read C2 somewhere here. It comes to 1.55. 1.5 is the line without number. Slightly more than that somewhere here, 1.55. Similarly, M value should be taken on the left side of the graph, 2.5. 2.6 is more than this. Touch the M line here and read the value on the y-axis. It is more than 0.6. 0.7 is this line without any number, and it's more than 0.7, less than 0.8, somewhere 2.6. Touch this line, read the value on the y-axis left side, 0.75 approximately I have taken, corresponding to d0 by di, 2.6, c1, c2 and m values we take from the graph. Then knowing the value of sigma I, we take this equation for sigma I 20-20 allowable stress sigma I. There is one unknown called deflection y in this equation. We find that I have put in the pink color here, y and y are unknown. We put the we substitute all other values in this and find the value of y. We get a quadratic equation. When you open the equation, you get second degree equation, and simplify that equation and find two values of y. Y you get as 16.17 or 0.775. We know that maximum value of deflection equal to the dished height 5 mm. It cannot be more than 5 mm in this problem. The dished height is given as 5 mm. So this is ruled out. This y is not correct. What is possible value? 0.775. So we take that value as y, 0.775. Then substitute that in the F equation, find out the load that is causing this deflection and stress. All the values we know, y, everything we know, substitute all this and find out the value of F here. Then outside stress also, we use this equation. I told you there is a negative sign here, otherwise everything same. So we find the outside stress also. So knowing the inner stress, we found the deflection. From deflection we went to force, and after that stress at the outer radius we found out. That's all the problems. Thank you very much. I'll do next video will be on leaf springs, which we will do after some time. Stop.